In this video, I am going to talk about the possibility of faster than light communication. So one question that naturally comes up when we think of superluminal causality is whether we can have superluminal communication. So we've been talking about Bell's inequality and how experiments of it show that non-locality is something that any quantum theory must have. And so the natural thing to always think is, does that mean we can communicate faster than the speed of light? And so the no communication theorem says that we cannot. And so I'll be mostly following the Wikipedia article on this here. But let's say that Alice and Bob are some distance d away from each other with entangled particles, the system of which has this underlying Hilbert space here. So it's just the tensor product of their two subsystem Hilbert spaces. So the density operator, which is sigma for the composite state of Alice's subsystem density operator A and Bob's subsystem density operator B, is given by this right here. So this is sigma. Alice performs a local measurement on her subsystem. In general, this is described by a quantum operation on the system state of the following kind, where P is a projection operator. Up here before the measurement, both of them have this mixed state, so the sigma mixed state right here, which has a half probability of being spin up and a half probability of being spin down. But then once Alice makes a measurement, we do the projection operator on this density matrix, and so Alice's ends up as spin up and Bob's as spin down right here. And so we have this as our projection operator right here. So we have these V sub k, which are the Krauss matrices, and these are just a mapping from our density matrix to the projection operation on the density matrix. And these I sub hb here is the identity matrix, and that's used because Alice's apparatus does not disturb Bob's subsystem. So if the combined system is prepared in a state with density matrix sigma, and immediately with no time delay after Alice performs her measurement, the relative state of Bob's system is given by the partial trace of the overall state with respect to Alice's system. And so the relative state of Bob's system after Alice's operation is just the trace here of the projection of the density matrix here. So this right here is just the partial trace mapping with respect to Alice's system. We can then show that the relative state of Bob's system with respect to Alice's system is the same as Bob's system prior to Alice's measurement. And so this is kind of the proof here. I'm not going to go through it in detail. The take-home message here is that we have the trace here of the projection of the density matrix, and that will end up being just equal to the trace of the density matrix. So we're saying that the trace right here before the measurement is the same as the trace right here after the measurement. And we can actually see that here with these density matrices. So we have 1/2 times this matrix, so the trace would just be half plus a half, so that equals 1, where here we just have the trace as 1 plus 0, which is just equal to 1 again. And so from this, it's argued that statistically, Bob cannot tell the difference between what Alice did and just performing a random measurement, or whether she did anything at all. So for instance, like I said, we have this as our density matrix, and so the trace of that is just 1/2 plus 1/2 equals 1, and so the trace after Alice measures is this with the projection. We have now projected it here, and so that's just 1 plus 0 equals 1. So the upshot of this proof is that Alice and Bob are attempting to communicate using entangled particles, that Bob cannot tell the difference between what Alice did and a random measurement. So whether Alice has made a measurement or not, Bob would not actually be able to tell based on his own measurements. Somewhat more concretely, this is because Alice cannot choose which of the states her particle adopts, nor can she perform multiple measurements until she obtains the state that she wants, because after a single measurement the entanglement is broken, and 2, Bob could not know if Alice made a measurement without somehow communicating with her through relativistic, so less than or equal to the speed of light means. So for instance, let us say that Alice and Bob are attempting to communicate using a two-state system, such as electron spin or photon polarization. So this would be our entangled state right here. So if Alice gets spin up, Bob gets spin down, and if Alice gets spin down, Bob gets spin up. So this means that when Alice makes a measurement, she has a 50% chance of getting spin up and a 50% chance of getting spin down, and Bob, if he measured his system at the same time, would obtain the opposite. So if, say, Alice wanted to send some kind of message using like binary code or Morse code or something, using the spin up and spin down of her particle, she could make, say, 100 measurements and obtain probabilistically around 50% spin up and 50% spin down. Even if Bob so happened to be measuring his own subsystems at the same time, he would simply see probabilistic distribution of spin down and spin up. Only through some relativistic messaging could they even confirm that they actually had opposite spins, or indeed that they were even measuring at the same time. So perhaps instead Alice could measure a single particle until she obtains the state that she wants. Say spin up. Say she's trying to give Bob spin down, so she wants to keep measuring until her particle is spin up. And it was at some prior time it was agreed that if Bob makes a measurement and his is spin down, this means no, so the answer to some previously agreed upon question. While if he measures it and it is spin up, this means yes. So they can communicate using yes, no to maybe some previously agreed upon question that they're trying to answer. The issue with this is that once Alice makes a measurement on her subsystem, the entanglement between those subsystems is broken. So subsequent measurements on her subsystem will not have the entangled interaction with Bob's subsystem. Thus, Bob will get whichever one occurred on the first measurement with 50% probability up and 50% down. But any subsequent measurements that Alice makes on her subsystem will not actually be reflected in Bob's measurement. But you might think that maybe they could communicate based on just whether or not Alice is making a measurement. So Bob can make measurements on his systems and see whether or not Alice is making a measurement on hers. So maybe Alice and Bob want to send a simple message about whether or not Alice is making a measurement or not. So if she's making measurements, this means yes, and if she's not, it means no. So let's say that both of them have a bunch of entangled particles. They can send their entangled particles through a double slit-like experiment, and if Bob gets interference, it means Alice is not measuring her subsystems. But if Bob does not get interference, it means that Alice is measuring her subsystems. So in this experiment, we can say that we have a Stern-Gerlach magnet with a double slit behind it, so that these spin-up particles go through one slit and the spin-down go through the other. If we have a single non-entangled particle, it will have a superposition of spin-up and spin-down, so it will go through both slits and interfere with itself. This will result in an interference pattern. So that would look like this up here. So we're sending a single particle through this magnet right here. It has a superposition of spin up and spin down. So it goes through both slits here and then interferes with itself so that we end up with an interference pattern. And so we're saying that if we then send this through and we somehow know which way it goes, so say it goes spin up, then there will be no interference after the double slit. It will land right here. If it's spin down, then it will definitely land right here, and we do not get an interference pattern. So now let's say that Alice and Bob both have one of these Stern-Gerlach double slit setups so that they can send their subsystem through. We might predict that if Bob is sending his subsystem through the apparatus, he will get an interference pattern until Alice makes a measurement, at which point the interference pattern will go away, because that would mean that Alice's takes on a definite spin value and it will be the opposite of Bob's. And so we would predict that we would then see the loss of that interference pattern from Bob's measurements. But this is not so. In the entangled system, upon sending his particle through the apparatus, Bob's particle takes on a definite state, either spin up or down with 50% probability, with Alice's taking the opposite, whether or not she actually performs a measurement. So it doesn't matter if Alice is actually performing a measurement or not, Bob's will take on a definite state and it will be opposite hers. And so since Bob's is in a definite spin state, he will not observe an interference pattern, whether or not Alice is actually performing a measurement. So that's what I'm showing here. So over here, I'm showing Alice as making a measurement, but it does not have to be the case that Alice is making a measurement. Bob's, say, he sends it through the Stern-Gerlach magnet here. If it's spin down, it will definitely be spin down, whether or not Alice is actually making a measurement over here. And so Bob will never see the interference pattern, and therefore he would not be able to tell whether or not Alice is actually making a measurement. And this is going to be something that happens in general, regardless of how we try to measure the interference that Bob we would predict might get. Because when we have the entangled states, then one will always take on the opposite of what the other one does, and therefore we always know what kind of state one is in because it is in the opposite of the other state. Another thing we might consider, though, is that if we have superluminal causal relations, as Bell's theorem says that we must in any quantum theory, then are these necessarily infinitely fast? So Bankal et al. In 2013 discuss superluminal but finite causal influences, so-called V causal influences, where V is some velocity greater than the speed of light but less than infinite. They say the experimental violation of Bell inequalities, so that's showing that we have to have non-locality, using space-like separated measurements precludes the explanation of quantum correlations through causal influences propagating at subluminal speed. So essentially saying that there are no subluminal hidden variables. Yet at any such experimental violation could always be explained in principle through models based on hidden influences propagating at a finite speed that just happens to be faster than the speed of light, provided v is large enough. Here we show that for any finite speed v, with v being greater than the speed of light and less than infinitely fast, such models predict correlations that can be exploited for faster than light communication. So they're saying that if it's not infinitely fast, then they could have faster than light communication. This superluminal communication does not require access to any hidden physical quantities, but only the manipulation of measurement devices at the level of our present-day description of quantum experiments. Hence, assuming the impossibility of using non-local correlations for superluminal communication, we exclude any possible explanation of quantum correlations in terms of influences propagating at any finite speed. A result uncovers a new aspect of the complex relationship between multipartite quantum non-locality and the impossibility of signaling. So in the end, what they say is, to conclude, we prove that if a V-causal model satisfies the requirement of reproducing the quantum correlations when the different systems are each within the range of causal influences of previously measured systems, then such a model will necessarily lead to superluminal signaling for any finite value greater than the speed of light. Moreover, our result opens a whole new avenue of experimental possibilities for testing V-causal models. It also illustrates the difficulty to modify quantum physics while maintaining no signaling. If we want to keep no signaling, it shows that quantum non-locality must necessarily relate discontinuously parts of the universe that are arbitrarily distant. This gives further weight to the idea that quantum correlations somehow arise from outside space-time, in the sense that no story in space and time can describe how they occur. So essentially what they're saying is that if we have finite superluminal communication, then we could explain this classically. But if it's infinitely fast, then we would have to have some theory that goes beyond space and time in order to explain it. And so what we were talking about here are just some considerations in a field known as quantum information theory. So this goes well beyond what can be covered in a single video. So an entire video series would be needed to cover quantum information theory. But I do have a few resources you can check out in the references down below. So these are some of the references I used in this video. These are some more references you can look at if you're interested in quantum information theory. And I do have a few videos here that also talk about communication at faster than light if you were interested in that. But anyway, I hope you found this video helpful, and I will see you in the next one.